Hey everyone, hope you're doing well. Today's video is all about transformations of functions. And the main idea is you have a base function, or you could call it a parent function. And then there are all sorts of kinds of transformations that you can apply to the function based on its equation. So you can see on the top right that we have three parent functions. We have a quadratic, a square root, and a rational function. For today's video, I'm only going to focus on quadratics just to help introduce the transformations. And then in a second video, I'll go over some other examples. Okay, so let's get started by looking at a quadratic. And I have a rough sketch of y equals x squared right here. So if I were to apply this onto the graph, this is what y equals x squared would look like. We have our vertex at the origin, and that's pretty much it. Pretty standard equation. What if I were to change the equation of y equals x squared? And if we look up here, I have four possible things that I could change. I could give it an a, b, c, or d value, and each one of those would change the graph in its own unique way. So let's actually start way over here with a d value. So instead of y equals x squared, let's do y equals x squared minus 2. And let's see how that would change the graph. So here's our original position. Now if I add the minus 2, I'm being shifted down 2 units where my vertex is now at y equals minus 2. And that is our first transformation that we can describe, or a transformation rule, where the value of d represents a vertical translation. In this case, our value of d was negative, so that means we had a downward shift. So what I'll do up here is I'll just make a note that this is a vertical translation. Some people say vertical translation, some people say a shift. Either word works. Okay, what if I were to add a c value? So instead of x squared minus 2, what if we did x minus 2 squared? Again, let's start with our parent function of y equals x squared. X minus 2 squared is actually going to give us a horizontal shift 2 units to the right. So now our vertex is at x equals 2. And that is our second possible transformation down here. So c represents a horizontal translation. However, the sign of the number is actually going to do the opposite of what we saw with our d value. So when d was negative, we had a shift downwards. So our value got more negative. However, with c, when we have a negative value, our x value actually becomes more positive. So again, x squared minus 2, our y values became more negative because it was a downward shift. X minus 2 squared, meaning we have a c value, was a shift 2 units to the right, making our x values more positive. So here I will say c is a horizontal shift or translation. Okay, let's look at a. And a would be a value outside of the brackets, right? So we can see that the difference between an a or a b value is whether or not this number is inside the brackets or outside the brackets of our equation. So a is outside. So let's say like a x squared, we could write that as a 2x squared. And what would that do to our graph? So a is going to be a stretch or a compression. And 2 means that we would have a stretch by a factor of 2. So technically, the graph is basically going to be stretched to be twice as long. And that's what that would look like. So let's go back to our original graph and look at our third rule. If a is greater than 1, you have a vertical stretch. If a is between 0 and 1, it's a compression. So we see up here, we had a value that was greater than 1, which is why we had a stretch by a factor of 2. But let's say this was 1 over 2x squared. All that means is instead of a stretch, we are going to have a compression by a factor of 1 over 2. And that's going to make the graph look kind of squished vertically. So we would say that this is a vertical stretch or compression. Finally, let's look at a b value. So let's write, for example, y equals 2x squared. So now our value is inside the brackets, meaning we have a b value. And this too will be a stretch or compression, but in the horizontal direction. And even though we have a value greater than 1, this is actually going to be a compression by a factor of 1 over 2. And that will look like that. So that will be our next rule, where if b is greater than 1, you have a horizontal compression, but if b is between 0 and 1, it's a stretch. And you'll notice that that is the exact opposite of what we do with our a value. So in the case of the b value, when it's greater than 1, it's a compression. When it is less than 1, let's say 1 over 2x squared, that would actually be a stretch by a factor of 2 horizontally, which would look something like this. And finally, we have the idea of whether or not our a or b values are negative or positive. If we have a negative sign on our a or b value, that means that there is a reflection, and the direction of that reflection depends on whether it's a or b. If we make a negative, that will be a vertical reflection. So let's see if I can do that here. Let's flip this vertically. So this would be the equation y equals negative x squared. And if I were to flip it horizontally, it's not really going to change because quadratics are symmetrical, but technically we could show that as y equals negative x squared, where the negative is inside the brackets. So okay, let's see if we can summarize everything we just went over. C and D are going to be translations. D is in the vertical direction, C is horizontal. A and B will be stretches or compressions, and I'll actually just write for B. A will be in the vertical direction, B will be horizontal. What you might notice is that the values inside the brackets deal with horizontal changes. So that would be B and C. And values outside the brackets are going to be vertical changes, A and D. You may also notice that values inside the brackets follow different rules than values outside the brackets. So let's look at our rules one more time. When D is positive, we have a positive shift. When D is negative, we have a negative shift, or a downward shift. However, for C, that is the exact opposite, where if we have a positive value, we're having a shift to the left, making our x values more negative, and vice versa with a negative sign. If A is greater than 1, we have a stretch, but if B is greater than 1, we have a compression. So that is going to be the main thing we need to focus on. That's what trips students up the most, is that difference between values inside the brackets versus values outside the brackets. And let's get some practice with that. Let's look at this equation. So our goal here is to describe the transformations that have happened based on the A, B, C, and D values. I personally like to start with the translations because those are easier to deal with. So let's look at our D value. We have a D value of 5, meaning that there has been a vertical translation up 5 units. And I'll just get rid of this arrow here so as not to confuse the direction of things. So, okay, first thing is the vertical translation up 5 units. Now let's look at our C value of -3. And even though it's a negative number, I know that it's kind of following a different rule because it's a value inside the brackets. So this would be a horizontal translation. Right 3 units. Let's now look at our B value. So our B value is in between 0 and 1. That means that this is actually a horizontal stretch. So this is a horizontal stretch by a factor of 2. So even though our B value is 1/2, we would say that the factor of the stretch is its reciprocal, which would be 2. And the same would go if we had a B value of 2, because when B is greater than 1, we actually have a compression, and it would be a compression by a factor of the reciprocal, which is 1/2. So just be careful when dealing with the B values. Finally, we have our A value. Even though we only have a negative sign here, we could kind of think of it being as a -1. So we don't have a stretch or a compression because our A value is 1. However, we do have a vertical reflection. Now, be careful when describing vertical reflections or working with examples with vertical reflections, because sometimes this will be described as a reflection in the x-axis. And this confuses a lot of students because you think, well, x-axis, that's dealing with a horizontal change. So shouldn't I say it's a reflection of the y-axis? But if we draw a Cartesian plane, if I have a quadratic up here and I want to do a vertical reflection, technically the x-axis is my plane of reflection. And I'll reflect it down here. If I had a quadratic here and I wanted to reflect it horizontally, the y-axis would be my plane of reflection. And so it would work out like that. So make sure you understand what the axis represents in terms of the type of reflection that's happening. That's it for the transformations on this equation. I just want to go over one other example. So let's write out an equation here. So you may look at this function and think, okay, I have a vertical translation down 4 units because of my d value. I have a horizontal translation 4 units to the left because of my c value. And then a vertical stretch by a factor of 3 because of my a value, and a horizontal compression by a value of 1, or by a factor of 1/2 because of my b value. However, something is not quite right with that description because I haven't factored out this 2 inside my brackets. So it's actually incorrect to say that our c value is 4. Because if I rewrite this equation, factoring out that 2 from our 2 terms inside the brackets, this is what I get. So our horizontal compression stays the same, but our c value is now a 2 instead of a 4. So make sure when you're given an equation that you have it set up like this as opposed to what's up here. So you want it to look like our example up here where we have everything neatly separated with brackets. Okay, that's about it for today. Thank you for watching. Again, check out part 2 if you'd like some examples of transformations for other functions, namely square root and rational functions. The logic is still the same, it's just that it's going to look visually a little different based on the function you're working with. Thank you for watching, and take care.